There we go. Okay. Okay, that's working. Okay. Thing there. This. There. Okay. Okay. Oh, let's see. I forgot to turn that off. Okay. Okay, time to get started. So here's where we were last time. We were talking about differentiability, and it's a bit of a weird conversation because it's a sophisticated discussion of anomalous, weird stuff, unrelatable in single variable calculus, and it seems like much ado about nothing. It isn't. It's actually really important in a full treatment of multivariable calculus, but it's not the focus of this course. We've got too much going on in this course anyway. Nevertheless, I think everyone should be exposed to how it's done and what the resulting answer is. So anyway, here it is. And we talked about it previously. It's about relative error and specifically vanishing relative error. Okay. Okay, so is this what we do in practice, day in and day out, when we need to establish a function's differentiable? Thankfully, no. There's a much easier method, as it turns out. It's this method of just looking at continuous differentiability. Now, this is a different condition. This is a stronger condition. Technically, there are some functions that are differentiable that are not continuously differentiable, and those are harder to deal with. Good news, we're not going to probably deal with hardly any, if any, of those in this class. So the beautiful thing about continuously differentiable functions is that it's super easy to check. Super easy. We'll see in a second. And any function that you, with great convenience, check is continuously differentiable, it immediately follows that the function is differentiable, which is very often the condition that you actually technically need. So it's really neat that there's an easy path to what would otherwise be a hard problem. So what is this continuous differentiability, and how can I identify it? Real simple definition: function is continuously differentiable based on looking at its partial derivatives. You got to look at all the partial derivatives and then just check that they exist, right? And that they're continuous. A little bit of a side note: how do you know if a function's continuous? I mean, we're not going to get rigorous about that in this class, but all polynomials are continuous. Trig functions, exponentials, logs, almost any function that you can think of is continuous where it is defined. And that's all we're going to need in this class. Now, you do have to worry about where it's defined, right? Obviously, not all trig functions are defined everywhere. So issues like that, but most vast majority of functions where they are defined are continuous. So pretty much take the partial derivatives, confirm they exist, declare them to be continuous, which again, everything we're going to deal with in this class. And you then know continuous differentiability, which then tells you differentiability, and you just saved yourself loads of trouble. Okay. All right. So for example, so I'll do it like this. Here's a function. Is it differentiable? Well, again, going straight at it from the definition, that's a hard problem. We've got to go back over here and think about, oh my gosh, what's the relative error, and what's the linear approximation, and oh my gosh. Right? But much more convenient, it's a polynomial. So all of its partials are polynomials, all of which are continuous. We're done here, right? It's that easy. So continuous differentiability, and therefore differentiability. Everybody with me? Okay, a couple other facts useful to know about differentiability. Every differentiable function is continuous. Doesn't go the other way, of course. But how we're going to use this is by taking the contrapositive. That's the, turn it around backwards and upside down. So if differentiable implies continuous, then not continuous means not differentiable. And so, for example, here's a function that we looked at previously, this weirdo there. Oh, whoops. Yeah, so I'll do it like this. This function, if I look at the origin, at that point, and if I want to know if this function's differentiable, well, it's not continuous. It's sort of obviously not continuous. It's got a clear sort of like jump discontinuity there at the origin. Not continuous means not differentiable. So resolved. Everybody with me? Okay. All righty. So moving along, we're going to talk about this is going to kind of put a cap on section 2.3. So what is this thing that we found called DF? We've talked about this previously as, well, it's the thing that works in the linear approximation. We've already observed that it's linear. Well, now, of course, it's linear because it's a matrix. All matrices are linear. But how should I think about it? Should I think about it as a notational convenience, which is what I kind of introduced it as? So the observation I'll make is this. This term right here and the formula for the linear approximation, well, don't forget the whole point. One of the defining characteristics of the linear approximation is that it agrees with f in value at a. So I can think of that as f of a, or I can think of it as L of a. And then I can take this and subtract it over to the other side. And what I get then is this formula where I have the change in L on the left, and then I have the change in X on the right. And said differently, we have the input differential on the right. We have the output differential on the left. To keep in mind what a differential is a linear estimate of change. So how much L changes is our linear estimate of how much F changes. So it's the differential. So I can rewrite all of this then as df and dx being related by this thing here. And this harkens back to our sort of, the very first thing that we said about derivatives. We were talking about, we had single variable derivatives previously, and then we say, well, we want to, generalize that to a multivariable setting. So what is the defining character? What makes something a derivative anyway? Well, it's a relationship between input changes and output changes. And check it out. That's exactly what the DF matrix does. It takes your input differentials and turns it into output differentials. Yes?
So that's the same thing that we discussed for literal pictures, right?
Yeah. Well, that's, it's morally kind of the same thing. So that's right. So that picture that you're describing, we were talking about that with partial derivatives. And so in that particular context, the partial derivative did the same thing. Absolutely. Here we're making a more general statement though, because this dx could be any. It's not just, well, only if you're moving in a single direction. But yes, morally, same exact picture. Yeah, right. Okay. Yes.
So is DF like a matrix? Or
yeah, that's right. No, it's this matrix. This matrix right here.
Okay.
Right. Remember, so it was a notational convenience when we were writing down linear approximations.
Right.
Yeah, absolutely.
And lowercase df is a
Lowercase df is the thing I was talking about before. It's our linear estimate to how much the function changes, right? In other words, looking at this formula, right? I was at the point A, now I'm at the point X. How much has this value, how much is our estimate of the value of the function different from our starting actual value of the function? Yeah, right. Okay. So yeah, so DF is the thing that relates input changes to output changes. It is and should be thought of as the derivative. DF is the derivative. And it's the general, this is really the best way to think about a derivative in a multivariable setting. So partial derivative by comparison is this, let's pretend we're doing single variable calculus, sort of like, I mean, it's not that we're done with that, but we're well beyond that now, right? We're understanding the derivative now as something that takes a vector as an input. All the variables can be changing, any or all can be changing. And looking at how the output changes accordingly. So DF is the derivative. And thus, by the way, why we use the letter D, which I was, cryptic about initially. We call it D because because it is the derivative. Okay, so we call it the derivative. Sometimes people are just to be a little more on the nose, they call it the derivative matrix because, of course, it's a matrix. Of course, also, it's a linear transformation, so it is routine to call it the derivative transformation. So this is just, heads up, you're going to hear these terms in this class, out of this class, whatever. And so they're all talking about the same thing. And then one other kind of broadening point, this matrix, this thing that I'm calling the derivative matrix, sometimes people want to distinguish between the linear transformation and the matrix representing the linear transformation. In fact, we did that in this class earlier, right? And so if you really want to distinguish between the matrix and the transformation it represents, sometimes people will use J to represent the matrix, and then we'll reserve DF to represent the linear transformation. But we're not going to make such a distinction in this class. This is really kind of no point in some sense. J for Jacobian, by the way. Jacobian for Jacobi, a mathematician who did some of this work. Okay. So yeah, here's a picture then, and I want to see if I can get this onto here we go. So this is a representation of what the DF matrix does. DF takes input changes dx, and then through the action of the DF matrix turns that into the DF differential output change. All right, so it turns input changes into output changes. Okay. Linear estimates, of course. All righty. Now, there's a different way you can think about this, and that comes from just taking this equation and just, this is going to seem too easy, but just divide both sides of the equation by dt. And if you do that, right, divide both sides of the equation by dt, then you can reinterpret this as, and this is a nice interpretation, that df is the relationship between the velocity that I'm moving with in the domain, and then the velocity that I'm moving with in the target. So again, I mean, it's the same story, right? I mean, this df is still what takes that vector and returns that vector. Sometimes, in fact, people just in recognition that the input vector, the vector could represent a displacement or it could represent the velocity, but the algebra is the same either way. So why make the distinction? Sometimes people will think about the DF matrix as relating input vectors to output vectors, and then interpret appropriate to your context, whatever. Anyway, okay. All righty. How's everybody doing? Everybody's happy with all this? All right. So you can make a similar argument when you're looking at real valued functions. Remember, for real valued functions, it was the gradient that was the thing that was involved in the linear transformation. So again, you can do that algebra to reinterpret the linear estimate as a relationship between input changes and output changes. I mean, same, right? And then you can reinterpret that as such. I mean, call this dx, call this df, and then now check it out. It's the gradient vector, specifically dot product with the gradient vector that's relating input changes to output changes. Now you could take this as, oh, well, then it's different in this case. For the vector valued version, it's the derivative matrix. For the scalar valued version, it's the dot product with the gradient. And if you want to think about that as being different, you're welcome to. I'll just point out that it's really morally kind of still the same. And let me go ahead and do that. Input vectors, output vectors, so same result. But check it out. After all, in this case, the derivative matrix looks like that, which really actually is, like turn your head to the side, right? I mean, it's the gradient vector. So the derivative matrix really is the same as the gradient vector. I mean, it's a matrix multiplication with the derivative matrix. It's a dot product with the gradient vector, but it's the same terms, and you're still multiplying by components, pairwise multiplying and adding. It's the same process. So choose to think of it whichever way you like. I like to think of dot product with the gradient as a kind of a geometrically friendly interpretation of what is actually multiplication by the derivative matrix. All right, does everybody see how they're kind of the same thing? All right, so, okay, there's a little bit of I'm just going to say an observation that has to get made here. By the way, in section 2.4, there's a bunch of stuff in there that I'm not going to talk about. It is all fair game. It is all stuff that you're responsible for. But it's various formulas and, algebra that's just a matter of kind of writing it down. And I don't think it's the best investment of class time for me to talk about those things. So anyway, make sure to go in and look at, notice, for example, there's a kind of a product rule and a kind of a quotient rule, etc. But anyway, like I say, they're in there, equations in the book. Take a look, make sure you understand it. But there is one aspect of it that's sophisticated and weird, and that's what I want to talk about. So we know that the derivative transformation is linear, right? Vector in, vector out, and then this process here, this process of turning input vectors into output vectors is a linear thing because it's a matrix. Okay. So the observation being made in the book that I'm going to explain is that while df is linear, d by itself also linear. So let's think about what d does. D acts on a function. D is something you do to a function, right? And then what do you get when you do d to a function? Well, what you get is a matrix of appropriate dimensions. So it's kind of weird to think about it this way, but d can be thought of as it's a function technically, but people like to think of it as such a weird function, right? It's not like it takes numbers in and gives you numbers out. It takes weirdo things in and gives you weirdo things out. And so people like to think of it as let's call it an operation or an operator, or if you want to think of it in whatever way you like, that's fine. But as a function, it is linear, as it turns out. And so now let's think about what that means. When we say something is linear, what we mean is if you do a linear combination in the inputs, then what you get is equivalently a linear combination of the corresponding outputs. Right? So this is what linearity means in this context, the linearity of D itself. So this is a true fact. D, about the, the act of differentiation, the act of taking a function and turning it into a derivative matrix. So just going to give you an example. Here's a couple of functions. I can write down their derivative matrices. No sweat, right? Taking the various partials. Make sure to remember, by the way, it's easy to kind of lose track with all that's going on, but this is what you get when you take the x partials, right? And then this is what you get when you take the y partials of all the various components. Okay, so anyway, function derivative matrix, function derivative matrix. Okay, now let's start playing linear combination games. If I were to take a linear combination of the functions, linear combination of the functions gives you this function, and I can take the derivative of that, right? So the d of this thing is, well, you take the x partials, you take the y partials, and you get this as the d of the linear combination. Okay, now let's take, though, instead, the same linear combination, right? 5 and 6, same linear combination, this time of the individual derivative matrices. And you see here, just doing that same linear combination of the individual derivative matrices. And, well, you can do the arithmetic there. And this linear combination is that. And sure enough, as promised, these two things are equal. In other words, the derivative of the combination is the combination of the derivatives. Yes.
18 and 24 be flipped to the top one.
Oh, look at that. Well, look what I did. Oh my God, shame on me. Yeah, God, how did I manage to do that? Let's see. Okay, let's think it through. Which one is this? Okay, so I need, let's see. Okay, what did I do here? What in the world did I do here? I think some of these numbers must be wrong even inside of here. Okay, so let's slowly and carefully. What is 5f plus 6g? Okay, 5f. So I'm going to have 5 times that, and then 5 times that. And now I need 6g. So 6 times that. 6 times that. What am I? Okay, I'm doing something silly here. I know this is silly. Okay, x partials. Y partials. What did I do wrong? What am I? This is crazy. Okay, well, maybe I messed up the. Yeah. Oh, yeah, that's what it is. Thank you. Okay, I'm sorry. Okay, so x partials. Oh, yeah, so that's right. So this needs to be a 4 and this needs to be a 3. Okay, thank you for catching that, y'all. Okay, so anticlimactic, but done correctly, these two things are the same. Okay, I will get that fixed in the notes and upload new notes right after class, right after office hours. Okay, so anyway, this is what corrected again. This is what we mean by the linearity of the D, not to be confused with the linearity of the DF, which is the more familiar concept. Okay. All right. So again, I already made this mention. There's product rule, quotient rule, certain conditions, blah, blah. You got to take a look at the book, and it's just algebra. Okay. Okay. So I'm going to move along. Talk about higher order partials. It's kind of like with higher order derivatives and single variable calculus that there are, if you take a derivative, then the resulting thing is a function and you can take its derivative. So here, for example, let's look at this function. Perfectly good function of x and y. I can thus take its x and y partials. And what's the result of taking the x partial? Well, I get this function, which is a function of x and y. And thus I can take its x and y partials, right? So it's just an observation that, well, yeah, you can do this. Now we'll talk about in a minute, what does this look like? What does it mean? Okay. First, I want to talk about notation. The notation is clunky, but having taken a partial with respect to x that we denote like this, the action of taking its y partial, we represent like that. Well, I mean, then a pretty reasonable notation, given that that's what we're computing, pretty reasonable notation would be, well, we seem to have two partial symbols, and so they write a partial squared. It's not squared, right? It's not a multiplication, but we write, it's just a notational, it's awkward, but it's a notational convention, and that's how people write it. And everyone knows that's not what it means, but that we write it that way anyway. And then likewise, in the denominator, there's a partial y and a partial x, and we write them together as if we're multiplying, which of course we aren't, but still, that's what it means. Okay, so y'all are going to see this notation to represent the y partial of the x partial. Everybody with it? All right. Now there's also the Newton notation, Newton-like notation. That initial x partial you can write as fx, which if we were to take the y partial of it and denote that y partial by putting the y as a subscript, as is the convention, right? Then notice we get this as the y partial of the x partial. And what's annoying, super annoying and confusing, is that here the first derivative that you took, namely the x, is on the right. Here the x is on the left, and the second up here, the second derivative you took was the y partial. It's on the left. Here the y is on the right. And that's just, I mean, it's just how the notations kind of fit together. They're a little ultimately the point is that we write the partial operator to the left of the function that we're taking the derivative of. We write the subscript to the right of the function that we're taking the derivative of. And none of this is my choice, so don't blame me. But this is just how it gets written down. Yeah, everybody good? Yes.
What is it like two vertical lines? Is that just
Oh, that's just a sideways equal sign. This is just, I'm saying this is equal to that. Yeah. So yeah, be aware of the notation. Okay, now you will have noticed perhaps by now that the y partial of the x partial and the x partial of the y partial happen to be exactly the same thing in this case. What are the odds? So is this a coincidence? It turns out it's not a coincidence. It's not even all that hard to show for polynomials that of course this is going to happen. It's just, you just write down the rules of how you take derivatives of polynomials, and yeah, it's just going to happen, right? But in fact, it's more broad than that. The order that you take partials, if a certain regularity condition is met, the order doesn't matter. So now what is the condition? The condition is that you need for, if you're gonna compare various kth partials, where you're taking partials with respect to, k different input variables, in succession. You need all of those kth partials to exist and be continuous. This is kind of a sort of beyond continuous differentiability. So I need not just the first partials, but the kth partials to exist and be continuous. And good news, again, most of the time, certainly all polynomials, that's true, right? And then again, just most other functions that we're going to deal with, this is true. And so most of the time, it's going to be the case that if you're taking partials with respect to certain of the input variables, if you rearrange the order in which you take those partials, you get the same thing. All right. Okay, so what do these things look like? There's the first step of what we're going to talk about there is actually pretty familiar. And so specifically, let's talk about the fxx, fyy. So we'll start with xx. It's about concavity, just like it is in single variable calculus. And the reason why, it's pretty easy to see that when you're taking the xx second partial, the very first thing that you do is say, I'm going to treat y like a constant and pretend that we're doing single variable calculus. And then you straight up do single variable calculus. You take literally a second derivative. With respect to x, of course, x is the only variable. Straight up a single variable second derivative of that resulting cross section. And well, we just already know that negative second derivative means that concave down. Now, concave down, but in which direction? Well, don't forget that in this process of computing that partial, it was in the x direction, namely y was to be treated as a constant. So this is in that direction. We're going in the x direction and y is a constant. So it's that way concave down. Everybody on board? And of course, you can imagine making the same kind of argument if you're talking about in the y direction. So fyy, very first thing you're going to do is set x equal to a constant. So you're just looking that way. X having been designated a constant. Now y is the only variable. We're taking a straight up second derivative with respect to the only variable. Of course, the only variable is y now. Second derivative gives you concavity. And so if, for example, as I have drawn here, if that second derivative, that y second derivative is positive, well, then in that direction, in that y direction, concave up. So I think that part is pretty relatable. By the way, let me brag. Isn't that a pretty good drawing there? You know how I did that? I literally, I'm not kidding. I bought Pringles, and I just it took me a while. And having done that successfully once, I've been kind of copying off of my own work since then. So it's not cheating if you copy off of yourself. Yeah. And I'll remind y'all, by the way, there is much to know about drawing, mathematical pictures, and there's tricks to know that will really help you do better. And I've carefully prepared and recorded over an hour discussion on the matter. And so if you are interested in getting better at making three-dimensional drawings, I do recommend that video. It's on my YouTube channel in the miscellaneous topics section. Give it a there's actually 2 recordings, but anyway, give them a look. Okay, that said, now let's ask the question, what about a mixed second partial? And this is not going to be relatable to single variable calculus, because there is no such thing as a mixed second derivative in single variable calculus, because there's only one variable. So this is going to be a brand new idea, and it's not going to be concavity. Okay, let's think about this one. We're taking an x partial of a y partial here. And so, okay, I've got a y partial, And I'm going to take an x partial of it. Fine. Better circle. There we go. So how do we visualize these things? The trick, what I think is the best trick for making sense out of this is to make different choices about how you interpret these two different partials. The y partials, I'm going to interpret as slopes of tangent lines to a graph. I guess I'm going to have to zoom out a notch here. Here we go. So here's me moving in the y direction in various places. Notice always in the y direction. As I move in those y directions, there's various tangent lines. I didn't draw the surface because it would just make the picture more cluttered. But these are various tangent lines to various, cross sections, all in the y direction, cross sections of the graph, and those y partials are those slopes. And let's kind of talk through what these slopes are. You can see that one is like really negative, and this one is somewhat negative, and this one is kind of barely negative, and then this one's about 0, and then this one's positive. Okay, so what then how am I going to interpret the x partial? I'm not going to interpret the x partial as slopes because I'm not looking at the graph of the y partial. I'm looking at the graph of f. The graph of the y partial is a totally different picture. It's certainly not what I'm looking at here, and I don't want to have to draw a second picture and then try to relate that to the original picture. It's just not going to be useful. So I'm going to interpret this x partial here as saying, all right, we're moving in the x direction. How fast is the function changing? So, okay, well, what sense can I make of that in this situation where I have these, for examples, slopes that started off being very negative and then slowly increased up to being, in fact, slightly positive? Well, as I'm going in the x direction, these y partials are increasing. So what we've done here is we've made a connection between the algebra of this mixed second partial and the geometry of this, for example, picture. And so here, I'm going to say that is positive because those blue slopes are increasing as I move in the green direction. That makes sense to everybody? It's a tough picture. Notice that this, what this picture, if you had to describe this picture geometrically, I would call it a twisting, right? It's like I'm kind of doing like, you can imagine if I'm holding a piece of rubber by 4 corners, it's like I'm twisting it like this, right? And so that mixed second partial measures a twisting of the graph. And the term that gets used for that sometimes is torsion, but that's just terminology. I like to think of it as twisting of the graph. All right. Okay. Yeah, all right, well, let's move it along. We are going to start in on the chain rule then, and I want to remind y'all about how to think about single variable derivatives. Correction, a way to think about single variable derivatives. Yeah, sure, slope of the graph, fine, not going to be that useful here. So let's think instead of a single variable derivative as, again, a relationship between input changes and output changes. And here I want to think of the changes as being velocities. So if I have some input velocity, x prime on the x-axis, and if these x values go into the f function and out come some y values, well, if the x values are moving, then of course the y values are going to be moving as well. I can talk about that velocity. And the derivative, dy dx, is the thing that turns that into that, right? It's the relationship between that input velocity and this output velocity. Is that cool? Everybody remember this point of view? Okay. So specifically about velocities, this just works better, I think, in this context. Okay. Now the diagram's going to get kind of hairy looking here in a second, but what you're going to look for, and I'm going to point out as we look at the hairy diagram to follow, you're going to look for this picture of input velocity, output velocity, thing that relates them is the derivative of the, the given function. Okay. All right, so here's the, yeah, okay, I guess that's good enough. So here I have a composition of two functions. I've got an f and I've got a g. F first and then g. All right, and we want to ask, what can I say about derivatives in this situation? And let's recognize, by the way, just for a moment, if a is the input, the starting value of x, well then f of a is the starting value for y, and then in fact g of that, so g of f of a is the starting value for z. So we've got these three different points. They're different, of course. They're different points. They're on different axes, so of course they're different points, and they're related by the functions as indicated. Okay, so with that observed, let's start by looking at this part of the picture alone. Forget about all the stuff on the right. F relates input values to output values. That's what the derivative does. That's just exactly what I had written above. Okay, next, let's look at this part of the diagram. G relates input values called y, gives output values called z, and so that's what the derivative does. Now, the function in question here is g instead of f, right? It relates y to z. So this derivative I would call dz dy, because that's what the variables are. Okay, and it relates, notice, input changes in y, output changes are z. So same thing that we did above, just different variables. And now let's look at, see if I can do this, that function. So forget about what's going on in the middle. Just think about the composition, G compose F, that takes X values in, gives Z values out. Yeah, there's an intermediate step. We're not talking about that, right? Right now, we're just talking about the composition where X is the input, Z is the output. Don't worry about what happens in the middle. And looking at this, well, the derivative, now dz dx, is what relates input changes and output changes. Okay, so I've written down, now again, kind of a hairy looking picture, right? But really all I've done is interpret the derivative 3 different times in a composition. And now there's just some sort of algebraic trickery here, where I'm going to observe that if I take this formula for y prime, put it in there, then this equation becomes that, which of course is the same as that, right? I mean, so the y prime is dy dx times x prime. Okay, so that's what I'm multiplying now by dz dy. It's just literally you plug in and you get this stuff down here. Yeah. And now I will compare this equation with that equation. I have 2 different things apparently that you can multiply by x prime to get z prime. How about that? 2 totally different, well, 2 seemingly, algebraically, at least at the moment, different things that relate x prime to z prime. Well, I guess those things must be the same. And so I get the familiar chain rule from single variable calculus. Everybody good? Okay. Here's another way to think about this. I mean, just kind of a intuitive kind of way to think about it. If you look up here, what turns the x prime into the z prime? Well, in this step, the thing that you multiply by is the derivative of that function. And then after that, you then multiply by a derivative of a different function. So one step at a time, you're successively multiplying, and therefore you're multiplying by a product. Whereas here, there's just kind of the one step. And so of course you're multiplying by the derivative of that function. And so of course those have to be the same thing, because in both cases we're starting with x prime, we're ending with z prime. And so therefore the product of these derivatives has to equal to that derivative. So that's another way to think about the same thing. A little bit more intuitive, a little bit less algebraic. All right, why am I showing y'all single variable calculus? And the reason is that this is exactly what's going to happen in the multivariable context. We're going to even get the exact same result, that the act of differentiation turns a composition into a product, just like in single variable calculus. And it's morally the same picture even. So here's what derivatives do in the multivariable world, right? Derivatives are relationships between input velocities and output velocities. Yeah. I mean, familiar, right? I mean, that's what we were saying here. A derivative is a relationship between input velocities and output velocities. It's just the only difference is that now the velocities are two-dimensional vectors instead of, you could think of them as one-dimensional vectors or scale, however you want to think about it. So I'm going to do the exact same argument. I'm going to look at a composition. Here we go. Here's a composition of first the function f that turns x's into y's. Then the function g that turns the y's into the z's. Now there's multiple variables in each stage, but still, okay. If the x's are moving, well, then so are the y's. And of course, if the y's are moving, well, then so are the z's. And I can try to relate these velocities, same story. How do I relate x prime and y prime? Well, by the derivative of f. How do I relate y prime and z prime? Well, by the derivative of g. How do I relate x prime and z prime directly, momentarily ignoring what's going on in the middle, whatever, x is the in, z is the out? Well, the derivative of the composition, because the composition is the function. So algebraically, I mean, it's set up the same way, and I even kind of combine in the same way. If I take this formula for y prime and put it there, right, then this turns into that, which turns into that. And, oh, well, I guess I need to be up here. And then I can compare this equation. I wrote it down. It's in a different location on the page here, but compare that equation to that equation. Both of these are saying what you do to x prime to get z prime. Well, if you're doing two different things and they do exactly the same things, then they're not different. They are in fact the same. And so look, highly analogous situation, practically identical argument, and morally equivalent punchline, which is that the derivative matrix of a composition is the product of the individual derivative matrices. So it's the exact same argument. So if you want to know why now, and it even rolls off the tongue the same way, differentiation turns a composition into a product. And why is this fact about matrix derivatives true? Well, it's true because it's morally equivalent to what happened with single variable calculus. Just kind of, now we're multiplying by, instead of multiplying by scalars, now we're multiplying by matrices, but we're still multiplying, and multiplication is associative, and so it's the same. Okay, I'm out of time. This is a good place to draw the line anyway. We'll see some examples and take it further next time. Let's see, that's Monday. Y'all have a great weekend. And a quick reminder, don't forget, we have an exam 1 week from today, if I remember correctly. Seems like we just started the semester, but we're already on the first exams upon us. And by the way, if anybody came in after I did attendance, make sure to come talk to me and I'll mark you down. No problem. Have a good weekend. Oh, sorry, y'all. I had my camera.
Thank you.
I forgot I had my camera little thingy closed. So anyway, but you couldn't see me, but you could see the screen. All right.